This is something I put together a couple of years ago, and I found it interesting as to how we've been applying electromagnetic techniques, or call it conductivity mapping, to looking for porphyries for quite some time, and yet we still, even after, and this image here is from a survey in Arizona in the early 50s, you know, we're 70 years into it, and we're still, like in this room, asking questions that seem to be fairly fundamental about what the physical properties are. Particularly, as was mentioned, we haven't really addressed the hypogene and supergene effects. And just in my own sort of personal endeavors in the last couple of years, it started to appear that geologists tend to be very comfortable with using terms like oxide or supergene, and they don't really, to me, differentiate what might be the underlying physical property differences. Even though the geological term might be the same coming from North America to South America, those differences can be vast. And that, from a point of view of looking at and understanding and interpreting geophysical data and having sensible communications with geologists, it's almost like, to me, I call it the analogy of cosmology, where, you know, geophysicists are often, to me, like the people peering through the Hubble telescope, and we're seeing things that people actually don't have an explanation for, the geologists. But we have to persist, I think, in asking questions that if we believe our data, if we think something is actually happening with the geology, if we don't explain it, at some point there has to be some conversations to extract that information. And I think one of the things that this collection here showed me anyways, that we are really good on the observational side, but we still kind of suck when it comes to explaining what we've got. And I think that that's really going forward, is that no, we shouldn't stop all our invention and new developments and things like that. That actually is a very exciting and important part of our business. But I think we do have to spend a bit more time and having these dialogues with geologists, because I think ultimately the challenge is what is the meaning geologically, and ultimately that then becomes what is the meaning from the perspective of exploration. Do we refine techniques? Do we need multiple techniques? Will airborne technique suffice instead of a ground technique? So anyways, people started energizing the ground with DC and electromagnetic fields early on, the modern era of geophysics, which was sort of starting in the early 50s. And we'll try and get the right. Do you have the?
You have to push the first arrow. No, on the computer.
Okay.
And then you can use the. Teaching geophysics how to use the computer.
Dick told, oh, okay, that's good. There we go. And when Dick saw this one, he says, no, that one's wrong. So I'm glad, I'm just going to skip right over that. He's already explained this in massive detail. It's not necessarily for this one. One thing that we will have here is a little bit of discussion about the enrichment. And I don't know if you want to lob in at this point, Dick, as to the...
Well, you're doing great.
Well, the bits in red, I don't understand them. Sean, help me. But no, this is really this is where the tire hits the asphalt, basically, because, you know, we see the shallow parts easiest with the highest resolution, and so whether we like it or not, we have to take ownership of the first stuff we hit. And if we don't understand it, and it's often the most complex because it's the interface between air and often weathered rock and fresh rock, it has the greatest dynamic range of physical properties. It's just the way the whole process works. And one of the things I found, and it'll become a bit later in this, with these enrichments, these are actually were meteoric events in the Miocene, where there was significant variation in water table. In South America, there seemed to be multi-phase events, but in North America, it was far less active. And so you see hypogene, or you see supergene in going all the way up into the Yukon and Alaska, but it doesn't look anything like the hypogene or supergene, sorry, in places like in Chile. But you don't see that in the geological papers, unfortunately. They may talk about percentages, but there's no attachment between the geological descriptions when you hear about them and what we potentially would see geophysically. So that's, I won't say that's a revolution. I'm sure a lot of people have figured this out, but the fact is that if it's not really put into the literature, then, well, one group, our younger people coming along, won't have a clue, will they? Because who's going to tell them that the world is much more different than the textbooks that they're reading? So I would say we do owe it to, if not ourselves, then the next generation. Curious scientists, Tony Berenger, in the mid-60s, took his very new input system down to Arizona. He flew a bunch of different places, and this was one, Cactus deposit, and it's suggestive here that he was getting some sort of response over a supergene enrichment, and that could be, in terms of a modern system, we really don't have any calibration. In fact, of what they to generate some sort of millisiemen response, we just see channel displays and deflections. I think the system ran at about 150 hertz or a bit higher. So this is for modern day technology, this is really probably not a particularly great conductor, but there did seem to be an anomaly sitting over top of this mineralization, but there was no context put into it. So we have an observation here, but nobody actually thought through what was being seen geologically. And I think Tony found that, well, he might have been intrigued with this. When he turned this towards massive sulfide exploration, the technique was far more effective, and that basically took control of how input was used. I didn't see until 20 years later any systematic efforts with Airborne for porphyry coppers. So that was kind of an assessment they made. This was the Mission deposit, and again they felt they saw some sort of geological response indicated by the one arrow, and then potentially a cultural one. So that's about as detailed as the comments get in the day. This is actually from a promotional manual that Questar put together. So it's not even in a scientific paper. These things didn't end up getting in Geophysics or even in the CIM bulletin. They tend to be just examples to try and hand out at the PDAC or what have you and get people to do more surveys. So and the Berenger group really wasn't, I don't think ever saw themselves as a research organization to educate other people. They were developing and they were trying to market technologies. So in a way, they fulfilled what their mission was. It was the rest of us that maybe didn't do a little more work. Ground EM was applied in the porphyry search in British Columbia in the 60s. It was successful in the Newman Peninsula, and they got a response which, in this case, was wonderfully labeled sulfide zone. Well, okay, we're talking 2 to 3%, 10, 15. My guess, there was also about 50 meters of clay sitting over top of the bedrock. So not bad for a system of that era. 1800 and 480 hertz system. So I suspect that could be 15, 20% sulfide in veins. It's not unheard of in these sorts of systems. So maybe they lucked out, because I know they ran it over others and they didn't get anything. So this one was somewhat unique, but it was a simple technique to use.
You think that's horizontal loop? What do you think that is?
Well, they were running with Crohn's shootback in some cases because of the topography. It's not captured in that section because in the day they didn't usually have topography or plotted in their profiles, but I know Duncan Crone put a system together for Noranda and it was used extensively in British Columbia. IP was also being experimented with in the 60s. This is an example that Chris Ludwig provided me from the Heinrichs GeoX organization over the Lakeshore Deposit in 67. And I think what people found was that even though Tony had his experiments, there was the success with the ground EM in BC, the American companies in particular felt that IP, both frequency and time domain, were probably going to be the most effective technique for the disseminated sulfide systems. So they basically put huge amounts of efforts into building technologies, operating them. I think at one time, I recall Anaconda had 6 crews out running. So they really it was truly what you call a full court press. This is a slide from some of Thoman's stuff showing IP anomalies over the Safford District. This was taken in the 1970s. I would think they probably would have technology, you know, with a 300-meter A spacing, and probably would have out to like an N1 through 4. They certainly didn't lack power. They had big generators and they could put a lot of current in the ground. But the receivers weren't quite up to the standards, I would say, that we have now. But, you know, you get anomalies, you act on them. So there's a string of chargeability features that obviously show a pretty big system. This will be part of what we're able to make available as one of Mark's presentations from a few years ago in the PDAC. There was a glimmer of light coming out of some work that the USGS did to the Santa Cruz deposit. When I say that, it's basically this chalcocite layer and DC resistivity log. There was some indication at the time that there was a conductive response coming out of chalcocite, but it was not really exploited in any sort of exploration sense. But I found it interesting that you can find evidence, and this dates back to the early 80s. We actually were starting to see effects of chalcocite and conductivity. We just didn't really have a model to attach to it. So, and that was also the time when basically all the American mining companies were being turned off, and the base metal groups were all being sold by their owners of the oil companies, and all the research groups were gone, all the staff was scattered to the four winds, and so even if you had information like this, it was going to be hard to act on it. This is a section that from an original 82 Zong survey over Escondida. It was the one line of conventional IP ever run over the deposit that before mining. So the Zong used it was about a 300-meter A spacing. Just gonna go. This is done. Here we go. So they had a 0.125 hertz. They got down to N6. Zong kindly, or Scott Urquhart kindly inverted this. It wasn't done at the time, or inversion wasn't available at the time. So the processing for a 1D smooth inversion was done in 2013 on this data that had been around for quite some time. So we seem to, with the resistivity across the top, seem to be seeing a bit of a conductive layer here that is interpreted, I think was likely to be the chalcocite blanket that existed at the time at Escondida. And then so those are the observed and inverted models. The inversion is at the top, and then we have the calculated data in the middle, and then the observed at the bottom. So that's what our resistivity looked like. And that was probably the most coherent of the signals. We have some on the chargeability as well, but the next image is from a later survey in 1985. Kennecott had retreated from the United States and was operating in Chile at the time, and with that operation they brought down their in-house IP system, which was the original system to operate the RIP, or reconnaissance IP approach. They basically set out these very long dipoles. There's one here, one over here, and then the orthogonal receivers were moved around. And there's the line that Zong was able to obtain for us over the what became the Escondida pit and deposit. But the Kennecott survey allowed us to see a much larger much larger area much more quickly. And it was sort of, we had the caliche problem, which was many people who worked in Chile are obviously aware of. And it was certainly alive and well in the early 80s when we did this. So that resistivity image, it's interesting. You look at the Escondida outline, the strongest connectivity feature is the yellow and the red, and it sits over what is very close to the new deposit found at depth on the southeastern flank of the Escondida deposit. So what we think we saw with the chalcocite blanket at Escondida was actually repeated in an experimental sense in the early 90s when Quantec Randall Nixon undertook a series of test surveys. One was at UJINA Rosario, one was at Chimborazo, and one was at Escondida Norte. And this shows what the original DC resistivity results at the bottom, which Quantec obtained for their client, and then Geonics TEM data sitting above. And so the idea that Randall had was that this data was very painful to obtain, but this was much faster as an inductive system. And so the conscious observation and connection between supergene and conductors, I think, was made at that point. BHP went on to exploit that. There's the geological model and where the supergene is. So it looked to be a reasonably convincing argument that we're mapping the supergene in that case. There was the one from Escondida Norte. This is actually done with early Airborne EM. Escondida itself wasn't available because it was being mined when the airborne system was available to fly in the early 90s. But the conductive response is pretty apparent. BHP then went on to fly a campaign using the CASA aircraft, and then later on the Megatem 4-engine plane. This was just decommissioned in the last couple of years, but they had major activity in Chile, which went on for, including follow-up, probably for over a decade. Another company that experimented with Airborne EM, and I wouldn't say it was driven explicitly by the chalcocite model, the supergene model, but a mapping approach was Noranda, and they flew the CASA on a number of campaigns in southeastern Arizona with the idea that they wanted to try and understand, I think, basin and range. They wanted to see if they could map structures, and they wanted to see if they could map some alteration. But when you read their paper, which they put in Geophysics, it was presented at AEM 98, there really wasn't any description of chasing a supergene or chalcocite blanket anomaly. I think they might not have, given the year and the Quantec work being in 92, they may not have settled on that as being something they could actually identify in this environment. But they did try Airborne EM. The fact that they published the results was quite helpful. And you can see here they're trying to interpret it in terms of the geology coming out of the EM data, which is good. But it didn't lead to any discoveries, and I think they refocused later on in the decade on their backyard in the Abitibi and applied huge amounts of Megatem to try and come up with more VMS deposits similar to Matagami, to the Horn, and to Kid Creek. So the porphyry era for them with EM was fairly short-lived. Frequency domain system was applied to the Sar Chesmah Deposit in Iran some years ago. This, I think, was who came up with the idea. When one never really knows, it's probably the people involved are no longer available to talk to or explain what motivated them. But this, to my knowledge, was the first one in Asia using this technique for porphyry coppers. As always in geophysics, responses were obtained, how useful they were. We have this annulus conductive zone around the porphyry system. It's pretty clear. But it appears to be a bullseye, but we don't, I mean, obviously it was after the fact that the deposit was known well before the survey was done, but a pretty interesting result, and one which maybe is, this has been floated around. I think Doug Pitcher showed this at the Northwest Miners, I think about 1992, 93, and the work had been done some years earlier. So certainly the community is aware of it. What they did in terms of acting on it, it's hard to say. Nobody points back to the Sar Chesmah. They go, ooh, ah, but it's been out there for 25 years. So it's, again, we have information, but it's difficult to know what action has been undertaken on that basis. Reykjavik in Pakistan shows some, Dick and I debated whether we included this. He had some Reykjavik images, but there's some, fairly discrete magnetic anomalies. In this case, they are bullseyes. The point I think he made was that it's not a one style anomaly story with these things. They also acquired some ground EM, and certainly unidentified this as a chalcocite blanket. So the weathering processes that were similar to what happened in South America clearly were affecting Pakistan maybe at the same time. You'd have to look at whether any research has been done as to when the supergene blanket was being created. Airborne EM, others tried it. Anglo flew their spectrum system over Rosario, UJINA. UJINA sits here. This is the one I was showing with the ground TEM and the DC resistivity, but Rosario also has a response. The ZTEM, ZTEM system came online in 2007, 2008, and the people controlling the technology at the time, Exploration Syndicate, although it's operated by Geotech, they had some style of commercial exclusivity for a period of time, focused on porphyry coppers, and this is one of the test surveys that they did in Arizona in collaboration with Phelps Dodge, and they started to show that we may have a technique now that would actually help us map porphyry systems in a way which magnetics alone really wasn't allowing us to do. So EM was sort of coming of age. IP wasn't being forgotten, but as the strategic value of airborne, I think, is obvious to most people. You can fly large areas fairly quickly. You can also do, you're working under open skies policies. You can fly somebody else's ground without their permission, if you so choose, in most jurisdictions in North America, except Newfoundland. This is an example from a porphyry moly system in Idaho. Red outline here is the pit. You can see what's pretty clear is the intrusive stock shows us this very resistive feature right in the middle. I have no idea why they clipped it here, but being in the US, it probably had something to do with some either indigenous people or some government issues on that patch, because most sane people would have at least gone over another half width here and covered that, but that's the way the survey was executed by the client. Example from central BC. This is quite close to the place that ground EM survey I showed from the 60s came from. Porphyry stock here. There's another porphyry stock down in here. It's a little more complex. With IP data that's also present on the property, we can see that these are all conductive ridges are all very correlative with resistivity features that have been mapped and show up very well with the DC resistivity. So fairly complementary set of structural and lithologic information in that environment. The one that Dick showed earlier, we have this conductive feature. My bet, John, it probably is sulfides. I mean, the acid thing could be correct too, or contribute. We probably worthwhile getting a bit more data on that. So it was encouraging to see. But of course, there were quite a few other anomalies. If you go back and look, there wasn't any lack of conductive features in the environment, and clearly the amount of drilling, there had to be decent mineralization in a number of these systems. It just, my understanding is the grades were better in this area. So the geophysics was actually lighting up a number of the intrusives that were mineralized, and I don't think it really told us uniquely that the one off to the west here was the best one. It just eventually was its turn, was my thought. One that turned up interestingly for me a few years ago was a find on the internet when we were compiling data over Coyahuasi, which is the name of the district that hosts UJINA and Rosario. And this again, like unfortunately a number of examples, a hard to find source because it actually was part of a financial presentation made to investors prepared by Glencore who are visiting the deposit. It's not a geoscience document. So these EM anomalies here are the work of the Glencore people, and they have defined these deep conductive zones underneath the porphyry that you can see here with these little glyphs. This is major copper zones greater than 10% associated with, at least with the conductor in here, and constitute a major part of the deposit now. This is, so this was flown by the spectrum, but the spectrum would have probably been not overwhelmed, but would have highlighted more of the supergene response, which also has a conductor that gives it in the near surface. This is down over half a kilometer and more. And my understanding is this actually constitutes the bulk of the economic part of this deposit right now. And this is very conductive. But there's no geophysical papers that discuss this. It's a word of mouth. Here is a 300-meter depth slice. And this shape here is quite interesting. Clearly there's some geological meaning behind it, but I also haven't found any geological papers in the last 10 years on this deposit. So while this knowledge has been out for over 10 years, there's really the owners have at least officially have kept fairly quiet about what the source of this conductivity. But again, I think, John, this is probably high sulfides. You're probably looking at 25% sulfides. My guess would be not possible. Well, then it's salt water, and then it's in a ring. So it's a. I mean, you have to think of what graphite. You got. There's only 3 or 4 things that can cause a conductor of that size.
That looks like the top of the pluton. There's a kilometer spacing between your red zips.
Right.
And if you look at cluster districts, that's the average spacing, 1 to 2 kilometers. Okay, between the apical zones, the cachos, the cupolas, and porphyry systems. If you look at the center of these things, they're about 1 to 2 kilometers, and that's your spacing there. So you're looking, I would argue that what you mapped is the top of the underlying bathymetric.
But that's not the reason it's conductive. We're looking at the conductivity, unfortunately, not the geology.
Well, but don't you have conductivity gradients between different rock types?
No, that's not a gradient. That's one honking conductor.
Ken, there is chalcocite veining, at 500 meters depth on.
Yeah, I think it would be veins. It's not a VMS.
Poderosa is a vein system, chalcocite vein system, and very wide. Mine is a massive sulfide. The reason you've got the hollow there for Rosario Oeste is that it's a hill, and we've taken a 300-meter depth slice. So, there is actually a conductor, if you've gone down 400 or 500, you would see that filled in.
Anyways, let's drill a hole.
They have. Well, you've right there. See? Those are all drill holes.
Yeah.
They've certainly tagged that part of it. So I mean, what you're saying, Mike, makes logical sense. The problem is, unless you've physically been there or talked to somebody. I mean, this is the way Benedictine monks communicated in the 11th century. You made journeys of many months to speak to one another, but it's like, I thought we did better than that. It's sort of like, you have this information out there, it's put in a financial document, logical reasons why these anomalies we can think of, but until somebody puts the observational information together. I mean, I chided my colleagues at Anglo who were involved with putting paper together at expiration 17, and I said, why don't you include this? Instead, they put the IP one in, even though it was a natural fields paper. You know, it was like, you missed an opportunity. I mean, unfortunately, I guess they considered it too sensitive. But it's public information because it's in the internet and it was provided to these guys from Frankfurt, you know, in 2006. So, anyways, thanks for the heads up. It's useful. The resolution deposit. This, my understanding, is this Quantec ran about 8 lines of MT in 06, 05, 06, and these results were shown at expiration 07. My understanding is the guy who showed them was let go when he returned to the office. They didn't want this shown, but it got out there. Subsequently, well, it was a few years later, it was flown and that anomaly revalidated. This is the sectional part of what Dick showed over Bingham, and I'm not sure if you, I didn't quite get, I don't think that contour anomaly, obviously it's the same data, so it's not contradicting it, but this is 2 kilometers down, and there's the heart of this very significant conductor, and they've drilled it. This actually has, obviously there's core somewhere in the greater Salt Lake area that has information about what they intersected. So, Dick, did anything in your brain matter?
Yeah, when you actually look at those sections, they drilled out the bottom of the copper into massive quartz. Lots of high volume percent quartz, but no copper. Copper's all higher up, and the QMP is probably the cupola zone of the stock from which the various dikes are coming off.
So
When
this,
is that done?
the drilling?
No, that section.
Oh, I would say it's been done over the last 6 to 7 years.
Yeah, so they drilled into the cupola. You see, they don't have any grade up there, do they?
Well, they don't discuss it.
There's a very, very sharp bottom of the copper.
We're talking.
focus. And, and then it's kind of like these fingers over an inverted cap over the top of the porphyry. And underneath the copper, right in the center, is the highest quartz vein density, but it carries no grade.
But quartz veins isn't conductive.
I know, I'm just telling you what the
Okay.
geology is.
Okay.
And
Yeah.
but that sits over the top of the composite stock which comes out of the cupola.
Yeah, I've asked the author of the paper what went on with that, and I mean the answer was there's clay, there's salt, or brine, there's sulfides. It's nondescript. I mean clearly they don't want to discuss it openly, but the fact they put 3 2-kilometer holes down.
Sure.
I mean 1 kilometer, one hole would have been curiosity. 3 implies they've got more than curiosity, because those would probably be $1 million each, even around the mine. Now it's interesting, that other anomaly is just that you showed on the contour, just coming in here. There's they've drilled that's near the mine gate. I think they call it the gate anomaly. But there's some mineralization at depth there, but they think the conductor is associated with a tuff. So there's, it's actually a low, high porosity volcanic that is given rise to that conductor. So, which is good. I mean, we can accept explanations. Mysteries are the annoying thing. This is one probably some of you have seen already. Some work we did on a casino porphyry in the Yukon. This is IP, resistivity in red, chargeability in green. But the MT gave a very clear anomaly down, topping out around 600 meters on the south side of the deposit. And this was one of the features last year that when I saw this, I said, there can't just be one of these. There's got to be more of these around. I mean, you have resolution, whatever's at Coihuasi. I'm not saying they're all the same source, but I'm just saying porphyry coppers are not just disseminated systems. There's frequently some connectivity of a much higher order of magnitude associated with them. And that can be mapped with technologies like EM, with magnetotellurics, to depths that are quite considerable. The implication for a number of the porphyries that some of my clients have brought in is these are up in Alaska or in the Yukon. Very, very difficult to develop financially because they're very energy consumptive. You have to move vast amounts of material, great distances. But if you have potentially a higher grade, smaller deposit, even if it's underground, you may actually have something to kick off an operation, or maybe a standalone mine by itself. So the owner of this property is, first of all, they asked me whether permafrost could have caused this. It was an interesting question. And I said, not likely, trying to be polite. But they didn't incorporate any of this into their advertising material, and now, I think last June, I saw this, this is now called their upside story, so interesting. So that's my graph, how we've gone through with the developments with porphyry systems. Initially we had some experimentation, 50s and 60s. IP became the dominant reptile in the mid-60s, and really, through the mid-80s, most of the work associated with porphyries would be centered around the use of the IP technique. But then we started to see the challenges, particularly in South America, with doing inductive or galvanic surveys, and so we wanted to have a better look at what inductive techniques could do, and that, I think, has brought us through a time now where we have sufficient observational information. We don't necessarily have a robust model, but I think we should have the confidence that using an EM technique, if well executed and intelligently executed, is not a fallacious strategy in search for porphyry coppers. So anyways, that's what I wanted to present, and those are my mentors and helpers that are so important in these things. And only one of them is a geophysicist. Oh, two. Well, actually, Mark's a geologist, so there you go. Thank you.